in. And obviously massive thanks to Josh for being with us tonight, and for Dale for hosting. So yeah, a bit of background on the event. For those of you that don't know about me or my business, my name is Barry Cranford. I'm actually the founder of the LJC. Actually, I'll run a little poll here just to see how many of you do know about me and the business and have been to LJC events. Good. Okay, we've got at least one person that is the first one ever. So as I said, I'm the founder of the LJC, and I also run RecWorks, which is a tech recruitment company. So at RecWorks, we are all about trying to find ways that recruitment can be a force for good in the tech industry beyond just getting people jobs. And what that means is that we're not just about getting people their next jobs, but we want to help people find a career that they really love, or get more people to find a passion for what it is that they do, and then help them go all in on it. So to give you a bit of a taste of what we do, we've built communities and user groups of over 10,000 people. We've run over 800 events, all learning focused, and 125 of those being in lockdown. And we've made over 3,000 mentor introductions. And so we do all this for free, or at least free for you guys. So how it works, we're basically paid to find talent, developers usually, and then we take a chunk of that and invest that back into community initiatives like this. So this year we've been doing things a bit different. We've set up what we're calling ladder groups, and they're an attempt to bring people together that are climbing the same ladder. So we've got the most established one now is the Aspiring Speakers, which is a group to get new people into speaking, hence talking to Josh there at the beginning. And we've had over 50 new people speaking this year. We've also got one for aspiring CTOs, and the latest group is the aspiring principal engineers. So people looking to improve their coding skills and take that step up. So if you want to become the next speaker, CTO, principal, or you just want to find a mentor, then reach out, let me know, hit me up on LinkedIn or Twitter or anything. And obviously, if you're hiring for tech talent, then please do bear us in mind. Anyway, on to tonight's event. It's going to be on reactive Spring. And Josh, as you heard him introducing himself a little bit there, Josh is the Spring developer advocate at VMware. He's a Java champion, the author of 6 books and numerous best-selling video training courses, as well as being an open source contributor and a podcaster. So Josh, over to you.
All right, thank you so much. So let me share my screen here. Okay. How do I close this poll? Good. Share my screen. All righty, good stuff. Well, I appreciate that. Thank you so much for this opportunity to be before you this morning, this evening, this afternoon. Obviously, I know there's a lot of places that we could all be right now instead of here, and yet we chose to hang out together. I love that. I love that. I love that. I love that we are in a community where we can just get together and talk about software, and it's just fun for at least for me. It's fun. I love this stuff, right? So thank you so much for joining us. A little bit about myself, as was just well explained. My name is Josh Long. I'm a Spring developer advocate, a Java champion, a Kotlin Google developer expert, and I'm online, very online, super engaged. So if you have questions, comments, feedback, as ineluctably I suspect you will, don't hesitate to reach out to me. I'm on Twitter. My direct messages are wide open at StarbucksMan. And of course, my email is josh@joshlong.com. I'm pretty async. It takes a while for me to get back, but I will do my level-headed best. And you might well find that my superpower is not that I know, which is very true. I don't know, right? But it's that I know who knows. And so should you have a question I don't know, which statistically, again, you might, I will know who knows on the Spring team. And that's one of the nice things is I'll make sure you get connected with whoever can answer the question best if I can't, right? So don't hesitate to reach out. Would love to hear from you. Always happy to engage. And of course, I recognize, I mentioned all this, recognizing how finite our time is tonight. I think we've got a couple hours maybe at most, so we're gonna have to hurry. There's a lot to get through. So with that, my name is Josh. I work on the Spring team. I have some training videos. These are available on Safari. I wrote a book back in 2017 called Cloud Native Java, which is all about how to build applications that survive and thrive in the cloud in terms of Spring Boot, Spring Cloud, and Cloud Foundry. The book it's out there. It's in American, not proper English, but hey, there's a with some effort you can translate, right? There's a podcast every Friday. That's, what is that, 2 days from now, called A Beautiful Podcast. There's a blog every Tuesday. That's yesterday. called This Week in Spring. And this is just a roundup of all the news that's fit to reprint. And there's a screencast every Wednesday, usually. And this is just me at a keyboard exploring the arcana of one particular thing in the ecosystem or another. And then finally, I've got this book called Reactive Spring. And that's what we're going to talk about today, my friends, is this book. So hopefully, maybe, possibly, you don't need to buy the book. Who knows? So what we're going to talk about is reactive programming in the context of Spring applications. Now, obviously, to have this discussion, we need to motivate what brings us to reactive programming. And for this, I think of three things. First, I want to, in the world of microservices, I want to be able to take advantage of microservices, right? And so to see why we care about that, to appreciate how we got here, I need to just draw very briefly this big picture. And if you've seen me talk about cloud native Java before, if you've seen me talk about testing before, then you'll understand that this is something I think about a lot, right? Which is, how do organizations go faster, right? How do we go faster? What is the thing that we have to do to be able to move software to production more efficiently, more safely, more robustly? And for a lot of organizations, we end up discovering something, whether quickly or painfully, we discover something very true, which is that organizations are mirror images of the communication structures of that organization. This is not new insight, right? That's Conway's law. And the implication is that if your organization does a bad job at communicating with each other, then the software that these different teams, these disparate teams build that need to talk to each other will reflect that dysfunction. That's a problem, right? So what you can do is you can optimize for better organizational autonomy, better communication, better independence relative to other parts of the organization. If you do that, you're doing what's called a reverse Conway maneuver. You're reorganizing your teams so as to better impact your software, to better affect your software. So the result here is, I want small teams. I want to take this large code base, I want to decompose it into small chunks. I want these chunks to be independently deployable. That part's critical, right? I want independently deployable because it allows me to build software independently of other parts of the organization. They did a poll where they asked folks at Google what they consider the most valuable aspect of their ability to deliver software and to deliver value to the business. And all of them pretty consistently cited autonomy. Their ability to move independent of the rest of the organization was the number one thing that allowed them to excel. So the most successful teams had and enjoyed autonomy, right? This is not new. Again, this is Conway's law. The ability for different parts of the organization to move independently of others is super important here. It allows them to iterate faster, to see a result and then iterate upon the result quicker. It's the OODA loop about which Adrian Cockcroft is so often spoken, right? Same thing for Werner Vogel. So you take a large team, decompose it into small ones. You have independently deployable, reusable bounded context. Well, what is that? That's a microservice, right? Independently deployable, it means it's a thing that's not linked in some static binary somewhere. It's actually deployed. What's the most natural way to do that? Over the network. What is the result of that? Well, now you've got network communication. And that is why we care about reactive programming, is because when you move to this microservices world and this client services world, both of which were, I think, we've seen the rise of both relative to 2007, 2008, 2009. When you move to that architecture and move to that world, some interesting things fall out of that. First of all, you have now a lot more network communication, right? And so, of course, here you have the question of resource efficiency, my ability to better repurpose the threads in my system, right? And this is a problem on a lot of different platforms because threads are expensive, right? The native operating system threads that Java uses for the moment, absent something awesome like Loom, are expensive. They're very expensive, right? And this is problematic because it means that we need to do our part when we write code to at least be conscientious of how we're using these threads and to, whenever possible, give those threads back to the runtime so that they can be repurposed for something else. So reactive programming is about writing code that at every single possible opportunity gives that thread back to the thread pool, to the runtime. Okay, so that's one thing I care about, is resource efficiency, especially in the context of microservices, because you'll so often see when you log into different data centers, you'll look at a computer in the cluster somewhere and you go, oh gosh, this thing is not accepting any new requests, and yet the CPU is idle. What's going on, right? Like these are this is a problem. And this is actually a really big problem when you consider that a lot of different people decide to let the platform's monitoring be the extent of their observation of the system. So if you rely on your Kubernetes cluster or Cloud Foundry or Mesos or whatever to tell you that your CPU is too high, you might find that it's never going to be too high, and you're going to think everything's fine. But what you don't see is that the threads are all idle. All the threads are parked in a waiting state, waiting for something to happen. What is it they're waiting for? Well, input and output, right? So much of the code that we use today was written in terms of Java IO input stream and output stream. So I say input stream.read, I ask for the next byte. As the byte arrives, I scoop up the bytes from the byte array, and then I put them into some sort of aggregation where I accrue them rather, and then eventually they get turned into a string or some record or whatever, right? Very, very basic input. But think about that contract there. I say input stream.read. I do this on the main thread. As I read from the main thread, I'm parked on the main thread. I can't move forward. There's nothing executing after that read call. And that's a problem, because there's actually an eternity in computer terms between when I'm asked for the data and when I actually get the bytes for the data, right? That thread could be doing something else, and yet it's stuck here waiting for us and waiting for these bytes that will arrive asynchronously, eventually over the wire, right? So what we want to do is to say, okay, I'm asking for the bytes, but they're not here yet, so I will give back this thread. That gives us a much better scalability curve, right? We can actually repurpose the same number of threads to handle many, many, many more transactions or requests per second. So that's the first use case that I care about, which is resource efficiency, right? Making the best use of the infrastructure that I've got, being a better bin packer, right? This is not a new thing, of course, and you've seen that there have been corresponding sort of evolutions in different aspects or different corners of the ecosystem. Certainly, the move to containers reflects this trend, right? And virtualization before that. So this is not new, right? We want to be more conscientious about price and cost, and this is one place where we can get a lot of cost. Okay, the next thing I care about is now that we've got all these microservices sat on the network talking to each other, conducting data over the wire, I care about how well they can communicate. What's the protocol that they use to talk to each other? Does that protocol give me affordances in the case of, in the situation where things will fail, should something fail, when invariably something fails, right? Things are going to fail. Statistically, the larger the surface area of your system, the more likely it is to fail, right? It becomes statistically more difficult to have a system that has 100% uptime, the more surface area that system has. It's guaranteed, right? If you think about Google, right? Google or Netflix or any of the FANG companies, right? Think about any of these companies, and you'll realize that it's been years, maybe even decades since they have had a day where nothing was on fire. Put another way, it has been years and years since nothing went wrong. It's been years and years since they had 24 hours without any issues somewhere in their data centers somewhere, right? Something's always broken at that scale, and that's okay, right? These organizations account for that. They embrace the realities of that failure, and they build systems to be resilient to that, right? These services don't often go down for everyone, and if they do, it's a freak accident and people put it in the news, because these things are built to be resilient, to be fault tolerant, to be scalable. So this is very, very important that we do that, that we care about that. And right now, the mechanisms that we have to build distributed services, they don't account for that. They don't give us any of these primitives that we need to be able to build these more tolerant, more robust interactions from one service to another. So that's the second thing I care about. And then finally, I care about ease of use. I care about composition, right? How easily can I compose different sources of data, different streams of data? This is very important, especially again in the context of a distributed systems world where you've got data coming from all sorts of different sources, right? What I want is some way to integrate all these different APIs. And absent something like reactive programming, I have to learn every unique API. This significantly worsens the learning curve. The on-ramp to productivity is particularly difficult here. So suppose I wanted to do HTTP. Okay, that's one API. I need to learn, right? Not a big deal. We've all done it, I'm sure. Suppose I want to do SQL database data access. Yet another API. What about eventual messages coming from RabbitMQ? Okay, yet another API. What about Apache Kafka? Okay, different API. What about WebSockets? What about service and events? Do you see the problem here? Every single one of these has a different way of saying, here are some records In some cases, they're not all here right now, but they might be here eventually. So you can hold on to this thing, or you can register a message listener container, or here's a future, or you can send a message, or you can just get this collection, Java util collection. All these are different ways of saying this code will get a different value every time it's available, some of which may be available in the distant future, right? We have to compensate. We have to learn all these different APIs. As you can imagine, that's bad for us because we're not great at like keep spreading our mental surface area over so many different spare things just to get the work done. And it's also bad for our code because it means we're constantly doing glue code or taking one thing and adapting it to another, right? And as somebody who's got a background in messaging and integration, I love this kind of stuff. But on the other hand, I don't love this kind of stuff. It shouldn't really be the case if whenever we can, we do something else, right? So reactive programming gives us a sort of grand unified theory, and I hate to invoke that because this is actually more practical than that. So we get three things when we move to reactive programming. We get ease of composition, we get a protocol for building reliable, robust services, and we get better resource efficiency. And these all matter that much more in the era of microservices, in the era of cloud native computing, because of these drivers that I've just talked about, the move to agile, to microservices, to continuous delivery, to test-driven development, to cloud native architecture. All of that is motivated by the need of different organizations to go faster. And so what we're dealing with is, in some way, a thing that we would have always had to deal with. It's always been there. But in other ways, it's something that's made that much more important because of microservices. These things go hand in hand. You can do one without the other, but you're going to find the experience less than compelling. So what I want to do today is, my friends, is we're going to go to start.spring.io and we're going to build some new software. This is my second favorite place on the internet. Anybody who knows me knows that this is my second favorite place on the internet. My first favorite place on the internet, of course, is production. I love production. You should love production. You should go as early and often as possible. Bring the kids, bring the family. The weather's amazing. It's the happiest place on earth. It is better than Disneyland. Not that we could go there this year anyway, but it's awesome. So since you can't go to Disneyland, and since you really, we can't go anywhere else, we might as well go to production. We might as well start here, start.spring.io. I'm going to build a new service. I'm going to go here. I'm going to choose, the defaults I think are satisfactory. That said, I would encourage you to inspect or to investigate Spring Boot 2.4.0. So you see the Spring Boot 2.3x line is really interesting. There's a lot of good stuff in Spring Boot 2.3 that further cements Spring's position of dominance in the cloud. To wit, Spring Boot 2.3 has support for readiness and liveness probes for Kubernetes. So you can actually you can have an endpoint that hangs off of the Spring Boot actuator endpoints, which are meant to support observability, that tell the container platform, in this case Kubernetes, about whether the service is A, ready to start serving requests, and B, still alive, right? So readiness and liveness. There's also support built in for Graceful Shutdown. So it's typical in a Kubernetes environment where you might have a pod that gets killed, and for whatever reason you do a rollout restart or whatever, and you have in-flight transactions. You have requests that are happening that you want to drain off before you shut down the pod. Well, you can configure Kubernetes to give your pod some time to gracefully shut down, and you can configure Spring Boot to do the same. So when it gets the kill signal, it'll gracefully shut down. It'll stop accepting new requests, and it'll let the in-flight transactions drain off. And you can configure the interval for that. It could be 30 seconds. It could be whatever you want, as long as you coordinate it with the platform itself. So there's now support for that in Spring as well. There's also super easy Docker container generation. So you can say Maven space hyphen spring hyphen boot, Maven space spring hyphen boot colon build hyphen image. That's it. It's just that simple. It uses something called Paketo, right? Paketo is a project from the Cloud Native Computing Foundation that allows you to take an app artifact, be it a .jar, .exe, or Ruby on Rails program, or Python program, or a .war, or whatever, and it'll give you a container that's got all the sensible defaults required to run such an artifact, right? So the result is that you can just take your Spring Boot application, run the Maven command, and it'll generate a Docker image for you that has a JDK in it. It has all the latest security patches. It's just sensible, right? It's defaulted to common things that you need to run a .jar versus a .war versus a whatever. And so there are different build packs that you can apply. A lot of times it just figures it out for you, but if you want to be specific about it, you can point it to any of a number of different build packs. And one of the really interesting opportunities here is another feature, which I think works best in Spring Boot 2.4. So that's why I was saying you should check out 2.4, which is the integration with the Spring GraalVM native project. Now, I don't know if you've paid much attention to GraalVM. GraalVM is originally a just-in-time compiler replacement, a C1 just-in-time compiler replacement. So something that could replace a hotspot, the code for which was mainly, as I understand it, in C++, and that became kind of gnarly. So they undertook the effort to rewrite much of it in Java, and the result is this new GraalVM just-in-time compiler. That just-in-time compiler has a lot of other interesting knock-on effects, which is when they got that code base and they realized, oh, okay, wait, this new just-in-time compiler produces more efficient code, it runs faster, it's very clean, it's easy to understand. Why not try something else? Why not do other things to see what we can do with this? And so one of the things they did was they said, well, we've got a just-in-time compiler, which again, when that first came out in Java, I remember I was blown away, right? That was a huge deal. Now, I think every language, even JavaScript has it, which is, you know, if JavaScript has it, it's not special by definition. But when it first came out, I was very impressed with this feature. The idea was I could take my interpreted bytecode, which is what we call compilation, and turn it into native code. Well, what if we cut out that middle step? What if we just proactively just took the whole source code tree, turned it into bytecode, and then immediately right after turned the whole thing into native code? Wouldn't that be more compelling? Turns out not so easy to do. First of all, it's hard to find code paths that can do that, because there are some things in the Java platform that are anathema to that kind of optimization. So things like reflection, things like loading jar resources, like a class path resource. These things are hostile to the process. So some configuration is required. What we've done is we built a plugin for GraalVM that gathers the requisite types and all that stuff and feeds it to the system so that it knows what it needs to do to compile a Spring Boot application into native images. Okay, so the result, I'm afraid, takes a fairly long time to run. The compiler is not fast. This is definitely not something you're going to do every single cycle, right? But you can do it in a continuous integration environment or whatever, and the results, I think, will speak for themselves. So here we go. I've got a code base, by the way. This is github.com, Josh Long, WebFlux, Actuator, GraalVM. You can check that out if you want for a very trivial example that has a web endpoint, that has a SQL data access with a reactive SQL database, and it has an HTTP endpoint and it has Actuator and all that. And yeah, whoop, target. Okay, there we go. There's Graceful Shutdown. Okay. Okay, there we are. There's my application. Starting up in not point 129, 127, depending on which line you're reading. So a tenth of a second and some. And remember, when I said I have a SQL database in there, I meant I'm actually embedding a SQL database. It is a SQL database, right? It's not. I'm not connecting. It's not just a client driver to connect to one. I'm actually starting up a SQL database in the application proper, H2. So, you know, really, really compelling results. I hope you'll check it out. There's two things out of this. First of all, obviously, very, very quick startup time. It's not uncommon to see applications that start up below a tenth of a second. And second of all, the memory footprint at runtime is nil, basically. It's almost nothing. So instead of Java applications that take hundreds of megabytes, you can have applications that take tens of megabytes of RAM and that stay pretty steady, right? You have a steady state memory usage for the balance of the time of the application. That's compelling. So if you're trying to build applications destined for the cloud and you want to win, this might be worth doing. I'm not going to say it's completely painless, right? There's still some things that may not work, particularly third-party libraries and certain projects in the Spring ecosystem that we've yet to integrate. But our goal is to make this. Our goal is to make all of this work well in time for Spring Boot 3 and Spring Framework 6. So that's the next major releases of everything. So we'll have, and you can already try it out now, right? So I encourage you to check out Spring Boot 2.4. But again, for our purposes, I'll stick with 2.3, okay? Because everything else we're going to see today works in a GA fashion, okay? Now, get back here. We're going to build a new application. We're going to call this a service. I'm imaginative, so I figured I'll use that name. And then we have down here a choice. We have what appears to be deceptively 3 different choices. It looks like we've got a choice of Java versions 15, 11, and 8. It seems like we have 3 choices, but my friends, we don't really have 3 choices. We have before us 2 choices, which are Java 15 and Java 11, and we have a non-choice. Now, that's not just a bread, okay? There's a choice here that we could make, but that we should not make. That is Java 8. Java 8 is a terrible decision. It's a terrible decision to make technically. It's less effective, less performant, less robust, less secure, less syntaxful, etc. It's also a terrible decision to make morally. You're not going to like the look of despair and frustration in your children's eyes when they realize that you're using Java 8 in production. Trust me, that's not a conversation you want to have. Don't do it. Just use Java 11 at the very least. Or if you are feeling, like you can, go to Java 15, as well you should. So we're going to use Lombok. We're going to use the reactive web support. We're going to use R2DBC, which is a SQL database activity, database abstraction. We're going to use Postgres, and we're going to use RSocket, and we're going to use security. Okay, so there's my my application. I'm going to hit generate. And which version of Java am I running, by the way? Okay, SDK list Java. And okay, CD downloads Java minus version UAO service.zip. Okay, first things first, it's a brand new application. We need to lock down certain things. We need to do the opposite. We need to remove the locks because there's certain things I don't want impeding our ability to do a demo, to see certain things happen. So we're going to remove those in just a second, assuming the index does its thing. This is what I get for not building something again after midnight. Okay, seems no, not quite. Indexing, scanning files, voila. Okay, so we go to the build, and the first thing I want to do is I want to comment out the Spring security dependencies because again, we don't need them just yet. We will later, surely, but not right now. So Spring Boot Starter Security, arrivederci, and Spring Security Messaging and Spring Security RSocket, ci vediamo. And okay, there we go. We've got our application. Maven, reload, good stuff. Now, our application is going to be a typical application. It's going to talk to a SQL data store. So as part of this, I need to connect my application to a SQL database. And I can do that in my property files, as always, with Spring. I'm going to use R2DBC. So R2DBC is a reactive relational database connectivity abstraction. It's just been recently donated to the Reactive Foundation, in fact. So that's cool, right? It's now a much bigger, broader effort. There are drivers, natively reactive, natively non-blocking, natively asynchronous drivers for Oracle, Microsoft SQL Server, H2, MariaDB, MySQL, Postgres, SAP HANA. I'm sure I'm missing something in there. Did I get Microsoft SQL Server? Yeah, I mean, there's a lot, right? And the numbers are growing all the time. So at this point, I don't even worry about it. I know there's things people can use. And the benefit here is that this API is written in such a way as to take advantage of non-blocking I/O. And so we'll see what that implies for us here when we write our code. Do I have my database running? That's the other thing that's important here. PSQL U orders. Yep, okay, good, happy. So first things first, we're going to build an application that writes data to the database. It's going to do so in terms of this ORM that we have. The ORM is going to map Java objects to database records, and I'm going to have a field here called ID and yet another one called name. And of course, this is Java, not Java 14 Preview Edition, but it's Java. And so I need getters and setters and all that stuff. And if I had Java 14 Preview Edition records, then I could use that. Certainly, if I was using any other language at all, I could also get that done. But since I'm not in any of those situations, I'm forced to use Lombok. So what I'm doing is here, I'm just synthesizing the getters, the setters, the toString, the equals, the hash code, etc. I'm going to signal that this is an ID column. It's going to be mapped to a primary key in the database using the ID annotation. And there you go. There's my basic entity. And I want to be able to manage the tedious, soul-annihilatingly boring read, write, update, and delete lifecycle for this record. So I'm going to use the reactive CRUD repository to map Java objects to reservations, right? Data in the database tables to Java objects of type reservation. And I'm going to use this repository interface to do most of that work. Now, this interface, I don't have to implement it. It implies certain methods that are very useful that Spring will make sure are available for us. So methods like save, save all, count, find by ID, delete, check if it exists, etc. All these things are implied. That should be fairly straightforward. What may not be so straightforward yet are the parameter types, the first of which is a publisher. Now, when I talk about reactive programming, it's very easy to understand the idea. I'm writing code in such a way as to give the runtime a clue about when I'm not using a thread. Very, very important. So look at the signature here, right? I have a publisher, a thing that produces data, okay? It has data and it produces data. It's not necessarily all there at the time you've got a reference to it. You can resolve it later, but it's there. And the way you resolve it is you say, I want to subscribe to this publisher, and you will pass in a subscriber, and the subscriber will be given a reference to a subscription when it first subscribes. But then as new records arrive, they'll be passed into the onNext method. They'll be passed into the onError method if there are errors, when ineluctably there are errors. And finally, your processor, your subscriber will have the onComplete method called when it's done being given data. Now, I kind of waved past this subscription thing. This is arguably the most important bit. This is what the subscriber is given when it first subscribes to a publisher. The subscriber keeps a reference to this subscription, and the subscription is used by the subscriber to request more or less data from the publisher. It does so by either requesting some number of records where n could be any number greater than 0, or -1 if you just want everything, in perpetuity, or you can cancel. The effect of this is that now, as a subscriber to a data store, I, as the consumer, have the ability to dictate the speed at which I consume that data. This is super important. Think about why we use, ignoring for now the principles of reactive programming, ignoring all that, just broadly. Let's just think about where we see this in other places, right? When you write low-level networking code, TCP, UDP networking code, you have to care about overflow, right? What happens when one message frame, when one producer goes faster than the other can handle, right? You have to care about flow control. This is natural at the lowest levels. At the large architectural level, the systems level, we care about this as well. This is why people use message queues, right? Store and forward architecture. The idea is that these message queues act as a natural buffer to absorb any extra load and then serially deliver those records to the consumer. That prevents the consumer from being overwhelmed. So at the lowest level, at the network level, we at TCP UDP programming level, we care about flow control. We have to write that code to make sure that one side doesn't get overwhelmed with the other. And at the systems level, the architectural level, thinking about disparate services on different networks, perhaps talking to each other, we use something like a message bus to make sure that one side can't overwhelm the other. Why is it controversial to support that in the everyday work that we do at the intervening levels? That's what the reactive streams gives us. It's not controversial, quite the contrary. We've had to think about this stuff for decades, right? Ever since there was one computer on the same network as another, we've had to care about flow control. We've just formalized that here. That's all. That's all we've done. We've put that at the top level API. So now you can exert control over that. So you can say, I want to ask for 10 more records. You're guaranteed no more than 10 records. You might get 1, you might get 5, you might get all 10 at the same nanosecond, or you might get one record every year for the next 10 years. You just don't know. There's nothing in the contract there. But the point is you will get no more than 10. So 10, if that's what you've asked for, is what you have signaled you feel you can handle in one fell swoop were it all to start being given to you immediately, right? It's just a matter of how comfortable you feel handling traffic or data. If you feel that this data has just been nothing but trouble and you just want to be done with it, you can cancel the stream. You can say, cancel, no, thank you, I'm done. So those 3 types are critical. Those are the absolute core of the reactive streams effort, a collaboration, a common ground effort between the Spring team, between the Eclipse Foundation, between Netflix and Lightbend, TypeSafe, etc. All these different organizations worked together about 5 years ago. We extracted out these common ground interfaces. There's a 4th one. Okay, a processor. And a processor is a bridge. It's a source and a sink, a publisher and a subscriber, a producer and a consumer. And that's it. Those are the 4 reactive stream types. If you understand those, congratulations, you're certified reactive. Go to Silicon Valley, raise $20 million, blow it all in lavish parties. You're ready. You're as ready as anybody here in the Valley will ever be. That said, I think we can agree that these reactive types, however useful, are pretty Spartan. They're pretty low level. I think we can agree on that, right? They're foundational. They're so foundational, in fact, that they've since been incorporated into the JDK. So you go to Java util concurrent flow, and you can see Java util concurrent flow.processor, .subscription, .subscriber, .publisher. These interfaces are in the Java 9 or later JDKs, like for like, interface for interface. The only thing that's different, of course, is the packaging. The package. And so you can use the flow adapters type, which is included in the Reactive Streams project, to adapt. You can take a regular Java JDK 9 publisher and adapt it to a Reactive Streams publisher and vice versa. So these types, foundational, very cool, but they don't give us the things that I want to be able to support easy operation and easy analysis of the data. So for this, we have 2 specializations. The first of which is a mono. A mono is a publisher, but it comes from Reactor. So this is different from the Reactive Stream spec. Reactor is a project that the Spring team built. A mono produces 0 or 1 record, at most 1. So you can use it to signal, I have this piece of data that will be here eventually, sort of like a completable future, except that it supports back pressure. We also have Flux, okay? A Flux is a publisher that produces 0 to n records, 0, 1, 2, 5, 10, a billion, a million, a trillion, infinite, whatever, right? There's no upper bound here. It could be just 3 records and you're done. It could be 3 trillion, you don't know, right? The point is, it's both these types of specializations, and they're both replete with operators. Look at these glorious operators. These operators allow you to do things like composition. They make it easy to build more robust services. So already those 3 points I talked to you about, can you see them starting to unfold here? We've talked about resource efficiency. You can see that by using these APIs, you're writing code in an asynchronous way. That's the queue that the runtime needs to be able to return the thread back to the system. You can see that we've got these glorious operators that I'm hoping you can see will start to support composition, things like map and flat map and zip. And we've got these operators that help make the interaction, the protocol between one service and another, and we've got the Reactive Streams APIs themselves that make the protocol, the interaction between one service and another, more robust, more scalable, right? So all these things taken together give us a huge win. So let's just see what that looks like when we just write regular code. I've got my repository, and I'm going to write some data to the database here. So I'll say class sample data initializer, okay? Initializer, okay, come on. Event listener, and this is going to be a bean that listens for an event. Public void, okay, void ready, okay. Component, and what we're going to do is we're going to inject the reservation repository here that we are using, and of course I want to synthesize that with a constructor, or synthesize that constructor with Lombok. And down here, I'm going to write some data to the database. So I'm going to create a reactive stream of people on the Spring team. So my friend Dr. Sire lives in London there, actually. He's on the Spring team. Obviously, there's Stefan on the Spring team, of course. There's Madura. She's on the Spring team, obviously. Olga, of course. Yushin, she's on the Spring team as well. We've got Violetta on the Spring team as well. We've got, who else do we have on the Spring team? I'm on the Spring team, for better or for worse, I'm there. And then who else do we have? Spencer, do we have him? I don't think we do. So what is that? That's 1, 2, 3, 4, 8 names. Good stuff. So we've got now a stream of names. I'm going to take each one of these names and I want to write them to the database. I've created a reactive stream of names, and now I want to visit each one and map it into a new reservation. So new reservation, null n. And that gives me a reactive stream of reservation POJOs. But that said, I don't actually have anything in the database. So I want to visit each one of those and save each one to the database. So I can say map dot, I could try doing map, I could try doing this, I could say reservation repository dot save R. But what happens when I do that? Well, consider what happens when you call map. Map accumulates the result of the inner lambda into a container type. So save returns a mono of reservation. So the result of this map operation is a publisher that contains a publisher that contains a reservation. No good, right? I want to unpack that intermediate type. So I say flat map, all right? Flat map. Good stuff. So now there is the pipeline that defines how I'm going to take a bunch of strings and write them to the database. The thing is, I haven't got anything in the database yet. If I were to run this code right now, assuming I go here and delete from reservation, if I run this code right now, we'd still see nothing has happened. The reason nothing has happened is because these streams are inert unless you activate them, right? They're pipelines through which water will flow. But if you don't turn the faucet on, then no water will flow, right? So I've got this pipeline, I've got the ability to see how water will flow, but I actually haven't started the water itself. So I have to say, I want to subscribe, and I can use one of the overloads here to, for example, listen to the results as they get trickled back. And so that would work. If I ran that code as is, I would see 8 names in my SQL data store. That said, I can already anticipate some problems. The first time I run this code, sure, yeah, it's going to take, it's going to write all 8 records to the database, and that's just fine. But what about the second time? I'll have 16 records, and the third time, 24 records, and so on. So this is not going to work, right? I want to, first of all, clean this up. You wouldn't normally tease out these intermediate variables in this way. You'd string them together thusly. And then second of all, I want to delete everything in the database first. Then I'm going to reset. So I'll say reservation repository dot delete. Then I'll say I want to save the names. And then I want to say this dot reservation repository find all. And then finally, I'll say I want to subscribe. Okay. Good. Okay. So there's my basic pipeline. I'm saying delete everything. And what you don't see, what's implied, but what you don't see is that I am saying delete everything potentially on a different thread. Okay. It could happen on a different thread. I'm saying delete everything. And then when you're done with all of that on whatever thread you do it, then and only then do I want to run this pipeline, the names pipeline. I want to write the data to the database. And then once that's all done, again, all possibly on different threads, once that's all done asynchronously at the very end of it, without with nary a countdown latch or cyclic barrier in sight, once that's all done, then I want to find all the records. And once that's all done, I want to then log out the results, all of which gets me what I want and gives me the most efficient version of what I want without making me compromise what I'm writing. I can just use this very simple deterministic sort of operator, these deterministic operators to get the result that I want. So if I run this as is, you'll see the records do the right thing in the database. Great. Now, naturally, I want to build an HTTP endpoint. So I could use a Spring MVC style controller. That's certainly an option. But I also quite like this router, this functional reactive style, right? So routes, return, route, build. And what I'm going to do here is I'm going to create an endpoint that returns reservations, new handler function. And I'll inject here my reservation repository, rr server response.ok.body rr.findAll reservation.class. What I've just described there is a reactive stream where I have a HTTP response that's being predicated based on this this predicate on the left, which is an HTTP GET request to / reservations. And when that happens, my little lambda gets invoked, and there's the entire response. I'm saying, here's the body. Each element of that body is a type reservation, etc. So that works just fine. A very simple HTTP interface. You can see it's also a builder API, so I could do dot delete and dot whatever if I wanted to, right? I could chain these things together. I could do a while loop. I could do for loops. I could do all sorts of dynamic things here to register HTTP endpoints based on configuration, based on what's in my database, etc. Okay, so I've got now localhost reservations. I've got 8 records in a database, and I've got my JSON and my HTTP endpoint. Who cares, right? I can imagine you saying, who cares, right? Why do I need this? I could have done this yesterday. I didn't need reactive APIs to read 8 records from a database and to give me 8 records in JSON. Quite the contrary. I could have done it just fine before. And that's true. What I'm trying to persuade you of at the moment is not the superiority of reactive APIs, but more the parity of reactive APIs. We have done what you could have done before in an API that's not more complicated than the Java 8 Streams API, and we've gotten a lot done in very little code. So let's get rid of this demo here, which is just for the purposes of our demonstration. get rid of that. And you can see my code is you know, a handful, literally a handful. So 51 to 42, that's 9. And then 34 to 29, that's 5. And then 6, 7, so 9 and 16 lines of code, including all these annotations, right? And the white space. That's 16 lines of code to get a reactive HTTP service that talks to a database. It's not more complex than anything you would have done before. It's not less approachable. It's not less readable. It would be, mind you, if you had tried to hand roll the threaded code that's executing behind the scenes here. That would have been a nightmare, right? You wouldn't have liked it, right? Remember, only one person truly understands how to write effective multi-threaded Java code. And it's not you. It doesn't matter who it is. It's not you. That's the important thing. I don't know who it is. It's not me, that's for sure. Don't do it. Friends don't let friends write threaded Java code. Let the runtime do the work for you. And that's what's happening here, okay? Now, also consider that we have one kind of API. Everything is a publisher. So if you want to describe this data that's going to come eventually, you can use a message listener container, or you can just use a publisher. If you want to describe HTTP data, use a publisher. WebSockets, use a publisher. REST, use a publisher. Service and events, use a publisher. You're starting to see what I'm saying here? One kind of API. So life becomes easy. If you can compose a publisher, then you're done, right? You're in the game. So now I've got this HTTP endpoint, and I've got this SQL database-based endpoint. It's not more complex than anything I would have done before. I get much better performance. But yes, point taken, right? I don't need necessarily reactive APIs to serve up 8 records from a SQL data store. Could have probably gotten by just fine on my own with Tomcat and the servlet APIs of yesteryear. That said, where reactive programming really comes into its own is when we start thinking about things that would have otherwise monopolized a thread. So let's create an endpoint here, greeting service. And this greeting service is going to return a stream of responses, okay, given a greetings request. So I'll create this type here, and this one as well. All right, and at data at all args constructor at no args constructor. Goody. Good. Okay. And the request is going to have in it a field called a name, and the response will have a message, private string message. And what I want to do is I want to create a never-ending stream. Okay. This never-ending stream, or well, actually, it's going to be finite, right? It's going to be a stream that we create to just generate new records, right? So we can see what's happening here. We're going to say new greetings response, hello request dot get name at instant dot now. Okay, good stuff. There's this. Place with lambda. Goody. Okay, there's my stream. Now, of course, this is an infinite stream. And if I ran this code as is, it would very quickly scroll down the floor and out the door. So what I want to do is I want to stagger the results a little bit here. And I also want to limit the results. I just want to take, let's say, 100 records or 10 records or something we can kind of keep in our head, okay? So I have now a service that's going to produce a stream of results. And notice that I'm able to do this. I'm able to introduce time into my stream because time is a dimension of my API. It's always been a dimension of my API. With reactive APIs, I can address that concern up front. And the reason I can do that is because behind the scenes, there is a scheduler. The scheduler is what handles the movement, the work, the scheduling of work on one thread or another. It's like our operating system for our reactive code. It handles that for you. You don't normally need to worry about it, but the important thing to keep in mind is that that scheduler relies on you keeping your promise. You cannot block a thread. If you do some work on the thread that blocks that thread, you're going to gum up the works for everybody, right? And so when I talk about blocking a thread, I mean anything like Java IO input stream .read, where you sit there and you wait for the result as opposed to being able to move forward pending some future result, right? When you block the result, when you block the thread, you're blocking a very finite number of threads. Beg your pardon. You're blocking a finite number of threads. So if you've got a scheduler and each thread is an event loop, and you've got 5 requests, you've got 4 cores, and you've only got 4 threads. Each thread is an event loop. It's going to handle as much work as possible. It's going to take work off of a work queue and just do it as quickly as possible and then put it back. As long as you're doing that, things are fine. But if you sit there and start doing something that blocks the thread, something like something algorithmic, like security, cryptography, right? Running Slack, Bitcoin mining, these are all algorithmically CPU intensive things to do, right? So as soon as you start doing that, you're monopolizing not just the thread for the one user, you're monopolizing a thread for, that's being shared by 25% of your users, right? So it's very important not to do that. We have a Java agent you can find called Blockhound. You add it to the class path, and as soon as you do something on one of these non-blocking thread pools that you shouldn't, it'll throw an exception, and you can then decide to subscribe to, or publish on or subscribe on a different scheduler. So subscribe on, and you can provide a different scheduler besides the default one, right? You don't need to know. You don't normally need to worry about this. It's just nice to know about, right? So execution service, whatever. Okay. Okay, so I've got this scheduler. It's behind the scenes. I want to turn this into an endpoint. I could create a WebSocket endpoint, surely, but I want to create a client that I can talk to with this. So what I'm going to do is I want to create an endpoint that I can talk to. And here we get into a discussion of what's the best protocol for service-to-service communication, and where do reactive APIs figure into this? Well, obviously, HTTP, not the best, right? Clearly, right? It's just never been the best choice for service-to-service communication. But it's out there. Certainly, it's an option. All right, it's definitely there. But consider all the limitations, right? Consider all the things that sort of flummox people when they try and use it at scale. First of all, if you're using HTTP 1.0, 1.x, it's porous, it's text-based, so that's immediately a problem. HTTP 2, of course, binary, so much better, but still not great, since a lot of people are still using 1.0. The connections are stateless. So you make a request to another service, you get a response, you disconnect. That's inefficient, right? I want to be able to maintain the connection and reconnect and just constantly stay connected, so I don't constantly have to do the connection and then the handshake and the hack and all that stuff. It's overhead that I don't want. HTTP 2, you can do that. You have multiplexed connections and long-lived connections, right? That's good. It's request response. That's it. You client makes a request to service. It's a client service protocol. It's not good, not great. We can do better, right? What about fire and forget? What about bi-directional communication, where once connected, either side can initiate the conversation? These things are harder to do in HTTP, and in some cases, like fire and forget, they're just not possible. So that's the first thing. Second thing is, what about all these other concerns? Well, different things like communication of data in an asynchronous fashion, right? Obviously, HTTP, not great for that, but WebSockets are better, right? WebSockets are certainly a better choice here. But even there, we've got an issue. WebSockets don't have headers. What are you supposed to do if you don't have a header? How do you propagate out-of-band information like a token absent a header in which to communicate that, right? So that's a problem. We want headers. This is clearly a use case for, real serious software, right? Or any software, just at all. So what can we do? Well, a lot of different organizations have tried to tackle the issue. Google, of course, famously, they created Grpc. Grpc is a way to create services based on Google Protocol Bus. It uses a kind of IDL, right? If you've ever did, Corba programming, as I did, or DCOM on Windows, as I had the unfortunate pleasure of doing once, never again. Then you'll know the idea, right? Or even SOAP, right? You've given a schema or some sort of definition of the service interface. You code generate your way out of it, and you get a response. You get a client and a service. Well, Grpc requires this. There's no way to do Grpc by hand, really. So people code generate their service implementations and their clients, which means that you've ceded control over how that API looks and how it works with the rest of your code in your organization. The resulting code, unfortunately, by default, is completable futures and things like that. It's not reactive. It doesn't support the use cases where you have a stream of data. So instead, I encourage you to take a look at Salesforce. Salesforce have a Grpc Protalk compiler plugin that will code generate reactor-based services. I like that much better. But you're still left with the other things, which is it requires you to do Google Protocol Bus, and it's not great, right? So what I want is something that supports all the different exchange patterns. I want something that has headers. I want something that is binary. I want something that has stateful connections. I want something that that lets me do whatever kind of messaging coding that I want. And I want something that I can write by hand. What can I use? Well, I also want something that's natively reactive on the wire, and I also want something that supports observability as a first-class citizen. Right? I want information about the stream itself to be accessible. So enter RSocket. RSocket is a binary protocol that was created by engineers at Netflix who then went to Facebook, where it now thrives. It's a protocol that is designed to scale to meet, well, Facebook's demands, right? Facebook's use cases. These are, and by the way, I live in San Francisco. They're, the Instagram building is like 2.5 blocks that way. You can see it from the corner of the street here. So these use cases, this use case, this protocol rather is a binary protocol. It is designed by engineers to support reactive programming on the wire, so it understands back pressure. This is in stark contrast to something like HTTP. Consider what happens when you have an HTTP service and an HTTP client. The client makes a connection to the service, and the client decides to disconnect. That's it. All that the service can do, all this reactive HTTP service can do, is on perception of the socket disconnect, apply back pressure to the streams that were involved in producing the response that was being sent to that client before it disconnected. That's it. It can cancel. It can call subscription.cancel, but one time. There's no way to just request 10 records and then an hour later request 10 more. There's no way to do session resumption as the Reactive Streams API implies you could, right? Well, with RSocket, you have that, right? So RSocket, you have the ability to actually have this protocol that extends over the wire. You also have the ability to push back. You have back pressure. You can say, I don't want any more data right now, but I'm not disconnected. I'm just not asking for more data, right? There's a difference. So this is a very interesting protocol. When I talk about observability, what I mean is it also supports a metadata frame specifically to communicate, health information, heartbeat information, metadata about the service health itself. This is not a controversial idea. If you've ever used Spring Boot's actuator, then you know that there are a set of HTTP endpoints that give you information about the state of the service, the health, the uptime, the metrics, etc. That's very, very useful in a Spring Boot application. But it's a convention in the Spring Boot ecosystem. It's not something that we all do, right? It's not something that everybody who's ever built an HTTP service does. Well, that's built into RSocket. So what we're going to do is we're going to take a look at RSocket. We're going to create a client. We're going to create a client for our HTTP endpoint and a client for our HTTP service. And here, we'll start to see where reactive APIs really come into their own in terms of scatter, gather, service orchestration, and composition, and in terms of building more reliable, more robust systems. So to do that, we're going to use Spring Security. We're going to use Lombok. We're going to use RSocket. And we're going to use the reactive web support. I think I already, Spring Security, Lombok, reactive web, RSocket. Did I already generate it somehow? Show in Finder. Okay. Good stuff. UAO. Client.zip. Now, before I get too far down the road, now's a good time to ask any questions. Let me take a brief pause here. I'll take a sip of water. I'd say we're about halfway through, maybe a little bit more than halfway through, but I do want to make sure I answer some questions. So I'm going to stop sharing and I'll take a look at some of these questions, and I'll share my screen again in a second. Okay, are there any questions? No questions. Okay. Okay, feel free to ask. I'm always happy to answer them. I just want to make sure that I'm not leaving anybody behind. Okay, back to this. Good. So we have our client, and this client is going to act as a thing that talks to our service. I'm going to do so through HTTP and through RSocket. Okay. So I've got this endpoint over here. I've got my service, and I want to create it. I want to create an RSocket endpoint out of it. So the first thing I'm going to do is I'm going to create a controller. Okay. So a controller, greeting controller. Okay. And it's just going to have an endpoint called greetings, publisher of greetings response, greetings request, return. And all I'm going to do is I'm going to delegate to my service implementation, private final greetings service at required args constructor, return this dot greetings service dot greet, passing in the request. So that's the whole RSocket integration. And the reason that was so easy is because when they built the RSocket protocol, the Java binding for RSocket was built on top of Reactor, the very same Reactor that we're using inside of Spring WebFlux, our HTTP API, or an R2DBC, our SQL database API, etc. So Reactor powers Facebook's RSocket Java binding. Okay. Now, we took that and went and took it a step further and built a nice integration to Spring itself. And the only thing that's required to make this controller do something, because it's otherwise inert, is that we have to actually stand up the RSocket port, right? So RSocket server port here, and we're going to say 8888. Okay, good luck. Good, so that's up and running. Now we can talk to this using our Java client, which we'll do in a second. But we can also use something called RSC. Now, RSC is a really convenient little project created by my colleague and friend, the one, the only, the amazing Toshiaki Maki from Japan. It's a RSocket client that aims to be curl for RSocket, and it is awesome. So RSC, and the way you do this is you specify the endpoint, localhost 8888. We're going to specify the interaction model. So again, we're sending a single request in, and we're getting a stream of responses back. That's called streaming, right? But if you send a stream of values in and get a stream of values back, that's called channel. If you do a single value in, but you get nothing back, that's called fire and forget. And if you do single value in and single value out, that's called request response, right? So there's interaction models that you have to be aware of, but that's cool because at least we have support for those, right? So RSC stream, the route is greetings, and the data that I'm going to send in, I'm going to do content negotiation here, is a name, right? So LJC. And there we go. There's my data. Every second in perpetuity, I'm going to get a new response back. And that's, well, not in perpetuity. I'll just get whatever I said, 10, 100, whatever. But the point is, I am now making a call. And in between the raindrops, in between each emitted message, which you can see is incrementing steadily towards infinity here. Did I not limit that? How many records do I have? Oh, 100. No wonder. I thought it was 10. I was like, wow, that's a lot. Each record, each response is given, it's emitted, and then instantaneously the thread is returned to the thread pool, and something else in the system is able to use that reactive stream. This is where you see some of the best benefits of using reactive APIs. I can now, in between the raindrops, I can free up that thread so that something else in the system can use it. Otherwise, this would have been lost. That thread would have been a lost cause. I would have had to wait to exhaust all 100 seconds of time before I got my thread back, right? Not a very scalable system. Now it's much more scalable, and I'm not writing markedly more complex code or anything like that. It just works. So I've got this reactive stream. I've got this endpoint. I want to create a client. You saw I can use the RSC client in the command line. I can also use the client. I can write a client here. And so in order to do that, first of all, I want to make a call to the HTTP endpoint. So I'm going to inject the HTTP builder. Okay. And I'm going to use that HTTP client, application listener, application ready event, ready, return event. Okay. And here, I'm going to inject the web client. So http.get.uri, http localhost host 8080 dot retrieve dot body to flux. And what I want to do is I want to take the data that I'm getting from the service and turn the JSON into a stream of reservations. So in order to do that, I'm going to do something terrible, something that you should never ever do ever, not even when you're all by yourself at home and no one is looking. I'm going to copy and paste code. I'll copy and paste that reservation, get rid of that. I'll get my greetings request and response over here, and voila, paste that. Good stuff. So now there's my details in the client. I can now cast, or I can convert, or, encode this JSON into a Java object, or decode it rather. There's my reservation. There's my stream. And so now I've got a stream of responses. What I want to do is I want to visit each one of those and write it out. So I'll say for each reservation, actually I just want to subscribe. I just want to write the results out. So I'll say subscribe, system out. Come on, Josh, you can do this. Subscribe. System out, print line, voila. Okay, so as results arrive, I'll get the results. Now, keep in mind, this is a client. It's not a web server. And so, actually, no, I have the WebFlux stuff there. If I didn't have the Spring Boot starter WebFlux stuff, nothing would start up a web server and nothing would keep the process running. So it's important that you realize that. Otherwise, you might, if you're just doing RSocket, you might start the application and it'll immediately start up and then stop before the asynchronous results have come back and you've had a chance to view them. So make sure you do something like system.in.read or something like that to keep the thread open, okay? Or join something. Okay, so now I've got this stream of responses. I've made a network call across the wire, and I'm assuming that this host and port are going to be there. Obviously, I should use something like the discovery client, the Spring Cloud discovery client, which gives me a service registry. The discovery client is very useful because it's a way to programmatically ask the cluster for the state of the system. How many services are there out there? How many instances of any one given service are there out there? And so on. And I can actually pull them. I can query for metadata. This is much more powerful than DNS because it gives me the ability to filter it, to query it, basically, as opposed to asking, where does this thing live? I can also ask, does this thing live? Right? That's a very interesting distinction. And a lot of different cloud platforms will give you the ability to treat them as a service registry as well. Kubernetes, of course, does the same thing, right? It has DNS, but that system of DNS is based on selector predicates, right? And so you can say, hey, based on whether these services have this predicate or not, I want to mark it as being available or not, right? So very, very natural thing to do. And so we have this discovery client abstraction. We can use it to do client-side load balancing. I haven't set it up here because I'm not, we're not doing that, but I could say reservation -service /reservations. And that host name would be replaced by the client-side load balancer in Java code with an actual host and port that corresponds to an instance of that service as discovered through the cloud's phone book, the service registry, the Rolodex of the cloud. Very, very convenient. That would mean that I would reduce the risk of hitting a dead node. Still, can we do better? What can we do to make this code more robust? Well, consider that I've got a reservation flux. Something might still go wrong, right? I've got some opportunities for failure. So I can retry. I can retry 10 times. I can retry when, and then back off 10 times, adding a second, right? I can do that if I wanted to. I can also provide an error handler. I can say, okay, when there's an exception, I'm going to return an empty stream. I'm gracefully degrading. This is super useful to do it at scale. And as you build scalable services, it's very important to have the ability to degrade gracefully, to say, look, I know you called the search engine service. It's not available right now, but here are some machine learned recommendations from across the web. So you can do this kind of thing. If nothing else, you can just return a generic, page not found or 404 error or whatever, right? You can return an error here. It's up to you. But the point is, you control how the service fails, not circumstance, right? You want to own what happens there. And that's very important in ensuring a good experience for the user. They'd much rather see your uninspired but useful, but available default error page rather than a big giant fat Java stack trace, right? That much better to give them this. So we can control how the service degrades. Very, very important in a microservices context. I can also do timeouts. Timeouts are kind of interesting, aren't they? I like timeouts, but why do we use timeouts? Why do we, imagine I had a super indulgent SLA of 20 whole seconds here, okay? Ridiculous. Who gets 20 seconds? That's an eternity in computer time. But imagine at this edge service, imagine this is not just a client, but it's actually a service that's, at the edge. It's a gateway service talking to the outside world. Imagine that I have just luxurious, indulgent 20 whole second SLA. I am obligated to get a response back to my client within 20 seconds. So that means that the things on which I depend, the things to which I send requests downstream, need to get back to me in 10 seconds, because if they fail, I can cut bait and try again and still get the response done in 20 seconds. Seems reasonable, right? Get one free mulligan, one free retry there. Good stuff. Okay, what about the service downstream? One hop after me, right? It's now got its own dependencies, and yet that dependency, same thing, it decays, right? So now it's half, it's 5 seconds that thing has to get a response back to it so that it can get back a response back to me within 10 seconds. What about the thing after that? Well, now 2.5 seconds. You see the problem here? We're very quickly forcing the downstream services into a more and more untenable position only by virtue of their proximity to the origin of the request. That's not great. We can do better. We must do better. So timeouts are not a great way to guarantee that we get a result within a certain amount of time, and they're intrinsically unfair. What we can do, another option, is to use something called hedging. Hedging, like hedging your bet, right? Don't put all your eggs in one basket, etc. That kind of thing. You want to diversify the risk by spreading the risk across a number of options. So what we're going to do here is we're going to use this aforementioned service registry, and we're going to ask it for some set of n distinct instances of the service in the service registry. I could say, give me 3 distinct host imports, right? It doesn't matter which, as long as they're available, as long as they're perceived to be available in the service registry, and then I can launch all 3. I can launch the same identical request to all 3 instances, right? To all 3 distinct instances at the same time in concurrence. So imagine, okay, using what we just learned, using this WebFlux, this web client API, imagine I call host 1, host 2, and host 3. Okay, so I've got 3 different host imports, and I want to get the results back. And again, I'll leave the null to you, right? But you can see what that would look like. It would just do it more of this, basically, right? You parameterize the URL there. But imagine I've got 3 host imports. I've got 3 pipelines. Remember, we haven't subscribed. As soon as we subscribe, then and only then will these 3 things start running, right? But they're not. There's nothing there. It's just 3 different pipelines, or 3 pipelines that will be eventually as soon as they're not null. Okay, but we haven't done anything yet. So we have a chance between when we've created the pipeline versus when we execute the pipeline to do some interesting things. We have the chance to interpose ourselves in that pipeline to reconfigure things. And this discrepancy is very intentional. In reactive APIs, you have assembly time when you assemble the pipeline versus runtime or execution time when you actually execute it. And one doesn't have to be even peripherally related to the other. I can assemble the pipeline yesterday and execute it 2022, right? It doesn't have, as long as the process is still running, there's no reason that couldn't happen. So you can do all sorts of interesting things in between, right? You can reconfigure things. And so that's where these operators play, right? They can take advantage of that opportunity to help us out, to rearrange things for us so that we get the result that we want. So here's one where I'm using the first operator. I'm saying, okay, launch all 3 of these subordinate streams, pick the fastest one, whichever one emits a value first, keep that one, and then apply back pressure to the other 2. Okay, so now I'm keeping the result that returns the result fastest. And the thinking here is, surely not all 3 of them are going to be down, right? One of them might be down, one of them might be out to lunch and garbage collecting. We don't know, but surely one of them will give me the response I want within my SLA. So whichever one that is, I'll keep it. And I could also still, at this level, I could still apply a timeout as well. So now I've got the fastest one, and I've upper bounded it to a timeout as well. And that's a very easy thing to express here, right? Imagine trying to express that otherwise. Imagine the multi-threaded code required to do that. That would be a race condition. It's not fun code to write, right? This is a very natural thing to express. And if you've ever done any low-level C code or something like that, this more or less corresponds to select, where you're given a bunch of file descriptors, right? And you can manage them that way. In the POSIX APIs, it's just a very natural thing to do here, right? I'm just saying, give me the first one that returns. Very, very convenient. So that's one thing I love about these operators, right? Another thing is that they make service orchestration and composition very easy. Okay, so let's suppose I'm going to imaginary API land here. Okay, so imagine I had a service or a CRM client that gave me 2 endpoints. The first endpoint gave me a stream of orders for a given customer ID. So private ID and customer ID. Okay, at data at all-args constructor, at no-args constructor. And the second one gave me all the customers. And so this is a different microservice. And I don't care, I'm not going to bother implementing those microservices. Let's just imagine. Okay, so I've got these, I've got customers, and customers have orders, but the order service is over here, the customer service is over here, and I want to get the results from both and compose them. So I have an interface client that is it'll give me access to both services and give me a unified view of the system, even though these are different services on different hosts and ports. So the first service endpoint is give me all customers, okay? And then the other one that we want is give me all of the orders for customer ID, right? Very natural. So here's my CRM client, okay? So now imagine I've got an implementation of this somewhere, and I've injected it here, and I'm going to use it to make a call to those services, okay? So again, just leave it to your imagination. It wouldn't be hard to put this together since you've seen how this looks. But now I want to say, okay, give me all the customers. That gives me a stream of customers. And I want to take each customer and turn it into an aggregate type. Okay, I'm going to create a new aggregate type so that I have a view of the system. I'll call this customer orders, right? It's neither a customer nor an order. It's a customer order, right? And so it has the aggregate types. It has the aggregate data. So private list of orders. Voila. Okay. Here's my list. Come on, list. Just when I need you. Good. Data at allRx constructor at noRx constructor. So here's my custom orders, and I'm going to visit each one of those. I'm going to say, okay, I've got the customers down here. I want to visit each one of those. And I'll say map each customer into a thing to hold both the customer and the orders that we're going to look up for that customer. So I need to hold both of them. So what I want is something called a tuple. A tuple is a typed collection, kind of, right? Where each element is a unique type. So I can do that pretty easily. I can say flux.zip. And zip, it's like a zipper. It given two publishers, one on the left, one on the right, it takes one from each side, okay? Well, of course, if you're using a mono, then there's only ever one to take from the left and only ever one to take from the right. So you can predict what's going to happen. So here, I'm going to return a mono with just the customer on the left, okay? And I'm going to return all the orders for that customer on the right. Come on. Mono. Okay, and of course, I'll say CRM client dot get all orders. Get orders for, rather, customer dot get ID. Okay, so there's that. Now let's see what that gives me. Okay, let's actually assign this to a variable here. There you go. I've got a flux of tuple of customer of order. Well, of course, we know what to do when we see a flux of a flux. Somewhere I forgot to do a flat map. Good, I can fix that here. Okay, now I've got a flux of tuple of customer of order. So that means that there's going to be a stream of tuple objects, and the tuple will have one customer on the left and one order on the right. Well, I don't want one order, I want all of them. So let me collect this as a list, right? Collect it as a mono of list of order. Okay, so what does that give me if I do that? Well, let's assign that now. That gives me a flux of tuple of customer to list of order. Okay, there we go. So I've now used this flux operator to stage the data in a place where I can now get access to both of them and then create the aggregate type. So now on the third line of this thing here, I'm going to visit each tuple, and I'll create a new customer orders object. Very easy. Okay, new customer orders. And then tuple dot get T1 is the customer. Okay, tuple dot get T2 is the list of orders. And that's my stream, right? See, I've now made two calls, or sorry, I've made n+1 calls. Keep in mind, this was actually one of the worst case scenarios, and you'll still find this to be quite performant. And the reason is because we're not doing it in a serialized fashion. We're not doing it 1, 2, 3, 4. We're doing everything at the same time. There's no implied dependency between record 1 and record 2, right? So we can get the orders for each customer at the same time. So we're getting all the customers, and then at the same time, on as many threads as possible, we're getting all the orders. Now, obviously, if you have only 4 threads and you've got 1,000 customers, then you might have to stack some of them on the same thread. So there might be some wait time, but this is as good as it gets, right? For this kind of service orchestration composition, things only get better from here, though, right? Because imagine you have an endpoint that gives you all the orders for all the customers whose ID you pass in, right? So now you can just sort it on the client, and that would be 2 calls, one for the customers and one for all the orders, and you get it all back in one fell swoop. And then that's easy enough to finesse into what you're looking for here as well. But the point is, this kind of processing, this kind of scatter-gather service orchestration composition, very natural thing to do in a reactive application. It's just, it breathes this kind of stuff. And because all the types are the same thing, we know what to do. It's very easy to get a result that you're happy with. Now, I'm using HTTP. Let's run this. I guess we should, I owe you that. Let's run this. And then let's look at the RSocket endpoint. That's the one I've been excited to look at, right? The RSocket client. So let's run this here. What was I doing? Oh yeah, HTTP. That's what I was trying to do. I don't need this toString. That was superfluous. Okay, run that. Oh, port 8080 is already in use. Of course it is. Application.property, server.port, 0, don't care. Goody, there's my data. As we expected, things are fine. Now, let's talk to the RSocket endpoint. This is going to be, structurally very similar to what we just did. No surprise. So, but in here, in the RSocket world, we don't use a client because again, there's no such thing as a client. In RSocket, once two sockets are connected, either side can initiate the conversation. Either side can ask questions of the other one at any point in time. So neither side is purely a client or service. Both can be a client or a service to each other, right? Or both at different times. So here's my RSocket requester. When I want to request something, I'm a requester. When I want to respond, I'm a responder. Either way, I'm going to use that here as before. RSocket. What did I call this down here? HTTP ready. Okay. Ready. Good. Turn event. And voila. There's my RSocket requester. RSocket requester. I'm going to inject that here. And now I can make network calls across the wire to it as well. RSocket requester. .route greetings. And then I want to get the results back. So I'll say that the data that I'm sending in is a new greetings request. LJC. Okay. Retrieve flux of type greetings response. .class, and that gives me a stream of responses. And then, as before, I can just subscribe to it. And fairly straightforward, right? Again, you've seen this kind of thing before. You've seen how we can work with APIs in this way, and we get this very sort of fluid builder experience. But that said, I'm basically doing RPC here, aren't I? I'm actually making a call to the service. I'm passing in parameters. I'm getting a response. It works. It's fine. But it is kind of RPC-like. And so recognizing that, my friend Mario and I had an interesting conversation a few months ago, and he suggested, wouldn't it be neat if we had some sort of RSocket, feign-like thing or retrofit-like thing? And so our little project, this thing I went out and built called Spring Projects Experimental, called Spring RetroSocket. It's on the experimental website. It's not GA. It's not yet done, but it works. And it's exhaustively documented and all that. And the idea is you just add the current dependency, like so. Okay, get the current version. Snapshot, great. And we need to add the milestone repositories, right? Because it's not yet GA. And then we need to actually enable this in our code base. So let's rebuild it, maybe even reload the project, go to the client here. And here, I'm going to say @enable RSocket clients. Okay. And once we've done that, we can now describe in kind of an RPC style fashion our client. So greeting client, publisher of greetings response, greetings request. Voila. And of course, this becomes, you annotate this with the server-side message mapping annotation. And it's an RSocket client. And that's it. You can now inject this into your code base. So you can say, OK, well, copy and paste that. Retrofit. Right, and greetings client. And here, client.greet new greetings request, LJC retrofit. And then, well, that's it. Actually, that's the entire stream, right? We're just going to greet it, and we'll get the response back, and everything else will be taken care of for us. And then we can print the results here. So let's say retrofit, RetroSocket. There you go. We start it. Okay, so you can see every second in lockstep almost, we're getting RetroSocket and regular one, right? From both the RSocket and the RetroSocket and RetroSocket client. So that's working as well, right? Fine. Now I like retrofit and RetroSocket. Obviously, I'm a fan, obviously, since I wrote it, but I will be the first to admit it's only good for RPC kinds of use cases. And you're missing out if that's your only use of RSocket. I mean, sure, it does a better job of RPC than HTTP or gRPC or whatever, but that's not where I think that's not one of the coolest features. To me, one of the coolest things you can do with it is to do bidirectional communication. So here I am in the client, but imagine my client has some sort of state that will foreclose on the service's ability to continue giving me data. Some sort of state, it doesn't matter what, maybe it's a game and I've exited the game or my character died or whatever, and I need to stop whatever is happening on the server from happening. Or maybe it's a chat application and I've disconnected from the chat, or I don't know, whatever. Maybe it's just muting notifications, right? I just want that to stop. I've got some sort of status check. So I want some sort of telemetry, some sort of information to come from this client that my service, the original thing that we built, can look at when it decides on whether to send more data to the client, right? So those greetings that we looked at earlier, there's 100 of them. But if the client's not interested, then we shouldn't bother producing 100 records. We should produce as many as we have and then just be done with it, right? So imagine I've got a controller, an RSocket controller here in my client. So again, my client's going to act like a service. It's going to act like a responder, not just a requester here. So I'm going to say client health state, private Boolean healthy, right? At data, at all-args constructor, at no-args constructor, and then class client health controller, at controller, okay, at message mapping, health, and here I'm going to just return a publisher of client health state. Okay, so I'm going to return a stream, return flux.fromStream, stream.generate, new client, new supplier, new client health state, math.random. So at some point it's going to be healthy, and then hopefully not too far. Hopefully we'll get to see it before all 100 records have been exhausted, but hopefully it'll turn to not healthy, and we'll see what's happening. And again, same thing, I want to stagger the results here a little bit so we can kind of keep up, otherwise it'll be instantaneous. So there's that. Okay. Take whatever, 1,000, who cares? Okay, so there's I'm simulating data, some sort of online thing, some sort of activity. I'm simulating that activity here on the client. I need to now mount that endpoint. I need for the client to advertise the presence of this endpoint that it has, that the service can talk to. So in order to do that, I need to customize this RSocket requester. So the client also becomes the thing by which we expose the service. So I need to inject a socket acceptor, and I need to build a socket acceptor. So socket acceptor, return new socket acceptor. I'm going to build a RSocket message handler dot responder, and I'm going to inject the RSocket strategies. Now in Spring Boot and Spring in general, the RSocket strategies is if you want to get a reference to how we're doing encoding or defaults and custom things like that, inject the RSocket strategies. That's where you would configure it, you would override it, etc. There's even an RSocket strategies customizer callback interface that you can use to override certain defaults there. I also want the health controller. Okay. Strategies, CHC. Good. There's my socket acceptor. And I just want to inject that here. So I'll say, okay, x dot acceptor SA. And voila. That's how you advertise the presence of this client health controller to the service. So let's run this. Well, actually, we don't want to run it yet. But on the service side, now, on my endpoint, I want to get access to that health information, don't I? So here, I have a stream of greetings to send back, greetings, right? But I only want to do so long as the health of the client is healthy, right? So here, I'm going to inject the RSocket requester from the client RSocket, right? The client RSocket connection. So this is a reference to the client itself. I can use that. I can say, okay, client RSocket connection dot client RSocket connection dot route health And just as before, I need to copy and paste. I need to copy and paste this health object, right, back to my service. Here we go. So I'm going to say, okay, route health, retrieve a stream of client health state dot class. And remember, what this is going to give me is a stream of health objects, but I don't want every single thing. In fact, I don't want almost any of them. I'm distinctly interested in the unhealthy states, right? I don't care about everything else. Everything else is fine. That's the status quo. That's what we're expecting. So I'm going to drop all of them by using a filter. The result of which is going to be that for the lifetime of this application, fingers crossed, right? Hopefully, this health stream will be empty. There'll be nothing in it, because as soon as something comes in, it matches that predicate. It says, oh, it's healthy, drop. So it'll never, if you put a subscribe on the next line, you say health.subscribe, hopefully you'll never see anything, right? But if you see anything, then something's wrong in the client. Something is bad, right? And in this case, our math.random went the wrong way and we're now unhealthy, right? But you can use that to say, oh, I don't want to continue doing something for the client because it's no longer there. It's not able to respond or whatever. So now I want to say, okay, return the greetings, but only so long as there is no health updates that we care about. See how easy that is to express? I'm saying, here's my stream of greetings, here's my ongoing concurrent stream of health status updates, and as long as this is empty, then I'll return the greetings. Otherwise, I'll abort. I'll just return. I'll no longer send anything. So now let's restart this service. Okay, there's my service. Let's start the client. Hopefully, well, fingers crossed. I've had some unlucky. I mean, sometimes I think I should play the lottery, but hopefully we'll see just a few of them, and then it'll fail. There you go. Bad health, right? So you got to 4 records, and then that math random went the opposite way, and it stopped the production. So my friends, hopefully you can kind of see now where we get some really interesting opportunities here. We've looked today at a number of different things. We've looked at building reactive data access with R2DBC. We looked at the basic motivations for reactive programming. We looked at the Spring data infrastructure for reactive applications. We saw how to use reactive streams types for doing basic data crunching and composition for creating reactive streams that we can use. We didn't really look at the NoSQL options, but keep in mind, we have, as I mentioned, a whole bevy of different R2DBC implementations, but we also have a huge catalog of NoSQL implementations. So reactive Cassandra, reactive Neo4j, reactive Elasticsearch, reactive Redis, reactive MongoDB, reactive Neo4j, reactive Google Cloud Spanner, reactive Azure Cosmos DB, etc. I mean, just the list goes on and on. So there's reactive drivers for anything you can imagine, really. And there are also reactive drivers for Kafka and RabbitMQ. So again, there's no reason to not use these reactive APIs since they're already there and they work for you, right? And it makes life simpler. Now you can compose these things. Again, imagine I've got a call of data from greetings, from the greeting service that's coming in over our socket, but this health state, maybe that's a stream of updates coming from Kafka, right? Maybe the client health state is something from Kafka. Maybe there's some cluster-wide thing where if there's a cluster-wide outage or whatever, then we need to disconnect. I don't know, whatever. The point is, the code would be the same. You'd have a flux of greetings response and a flux of client health state, and everything else would be the same. How you originated that flux might change, of course, but it's still a flux. So the same exact code, the algorithm works just as well. My friends, we've only begun to scratch the surface. I feel like we're at a good place to stop here, but we've only begun to scratch the surface. There's so much more that we could have done. Keep in mind, everything I showed you here is GA, except for that native image stuff, which is coming. It's already, you can already try that. Obviously, it's come a long way. It's already 2 years in R&D that we've already done, so it's getting better and better. And we'd love to go on the journey with you if you're interested. Everything I've shown you here is GA. I love this stuff because it allows people to build more robust, safer, more concise, more comprehensible services. That said, some people experience there's an uphill curve, I think, when you first learn these reactive stream types. That's true, that's fair. I can see that. But once you get it, you just kind of, get it. I hate to be that guy, but they're like the Lisp fanatic that just claims to have come down from the mountaintop, right? But once you've kind of done it enough, it just starts to make sense. And then you think, oh, I can't imagine wanting to go back to the other way. This just works. This is actually very consistent. And amortized over all the possible applications of these reactive stream types is actually less work. I have less to learn. I have to unlearn all this other nonsense because it's just easier this way, right? Once you've made that slight hill climb, you're in a much better position. And that's why there's a lot of energy behind reactive programming right now, right? So if you're using Kotlin and you're using reactive APIs, if you're using Spring and Kotlin, right, what you could do, you go to start.spring.io, choose Kotlin, you'll find that we have native support for coroutines built in. So everything that is a reactive stream can be used as a coroutine in Kotlin. How cool is that, right? So coroutines give you they give you kind of the best of both worlds. They give you the ability to describe a asynchronous thing like a reactive stream does, while writing code that looks imperative. It looks like you've got line 1, semicolon, line 2, semicolon, line 3. You've got that same, the code is written as though the thread stops right there at the line while the method executes. And it's not the case, right? In this case, even though it looks like it, what's actually happening is that the compiler has rewritten that method to actually execute separately. The thread is returned, the method returns, and then there's a continuation that packages up all the state after that asynchronous thing has executed, and then it gets invoked for you automatically. So it looks like you've got line 1, 2, line 3, line 4. What might actually be happening is you've got the first third of a function that gets executed, then some asynchronous thing, second third, then some asynchronous thing, and then the final third, and then and then you're done, right? That's really cool. It's syntax, it's a compiler syntax awesomeness, and a little bit of a runtime abstraction called a suspend function. Okay, when you understand this stuff, when you understand reactive APIs, coroutines are just natural. They're just a natural thing to do. And coroutines are Kotlin language ecosystem wide, so you can use coroutines in Android as well as on your server-side Spring applications, all based on this reactive API that you learned here. That's one thing that's really cool. The things I've just talked to you about, obviously they're tantalizing because they give you the ability to do more with less, right? In every sense of the word, financially, service-wise, infrastructure, code-wise, etc. There's no doubt that this is not a new thing. Obviously, Netflix has been talking about reactive APIs for years and years, and so on. Large organizations everywhere have been doing things with reactive APIs. The idea of reactive APIs itself is what, 13 years old now, 14 years old? I mean, it's a very, very old idea. And so a lot of big organizations have sort of flocked to it. We talked about Facebook, right? Well, well, not this year because it's 2020 and things are weird, but normally I spend anywhere from a few days to a week in Hangzhou, China. Now, Hangzhou is a few hours train ride from Shanghai, and it's the headquarters of Alibaba. So Alibaba is a small e-commerce engine in China. They're going to be big one day, and I spend my time bouncing around their various campuses, talking to folks about their uses of Spring. And I've been going there every year for, gosh, 9 years now. I mean, a long time, right? So every time I sit with him, I talk with him, I say, look, we've done this new thing on the Spring team. You might want to try this, might want to try that. In 2014, I went there and I said, hey, we're doing this thing called Spring Boot. It's going to be big. And of course, they've converged on Spring Boot, like crazy. It's everywhere now. And then ditto for Spring Cloud, ditto for reactive programming, and then finally for RSocket. Well, with RSocket, all that other stuff, they've been fervent contributors to the open source community. They, for example, maintain the Spring Cloud for Alibaba project, right? The same engineers that I know, that I talk to, are involved in that, for example. So they're always involved in open source, but the RSocket thing, I think, was a eye-opening thing for them when I showed them that. RSocket is now something they're converging on with Spring, of course, and they've actually joined us along with Facebook and others in creating this reactive foundation and working on RSocket. And RSocket became the first project that we donated to this foundation, along with Lightbend and Facebook and others. So all these different teams, all these different ecosystems, all these different organizations that have the money and the motivation to solve these problems by themselves if they need to, they've chosen to instead build on Spring or to build on reactive APIs, or to do both, build on Spring and reactive APIs. And they've chosen, in a lot of cases, to use RSocket as well. And so there's some interesting things being done in collaboration, one of which is a broker. Now imagine this RSocket application that I just described to you. Imagine I've got 10 different microservices deployed into a cluster. All of them, when they start up, they open up a socket to a hub. And the hub acts as kind of a gateway for outside requests, for requests coming in from the outside world, perhaps via HTTP or whatever. The hub takes the incoming requests from the outside world, or RSocket requests, keeps the socket open, And then it says, oh, you're trying to call this reservation service. Let me find a socket. Let me ask it how healthy it is, how busy it is. I can use that metadata frame to see what its uptime is, basically its availability. If it's not too busy, I'll send it your request. I'll forward your request onto it. If it is busy and there's nothing else available, I can apply as a hub. I can apply complete back pressure to the client that's making that request. So the client isn't disconnected. It's just waiting, right? And in the meantime, the client isn't blocked. It can wait for, it can do other things with the same socket. But the point is, it's first in line, and it doesn't feel like it's broken. It doesn't have to scramble, but it's also not getting a response immediately. But it's seamless. As soon as there is something available to produce a response, it gets patched over to that, because we can automatically route requests like that, right? So there's some very interesting opportunities there. Those services could be completely black box. There's no ingress whatsoever. Remember, those services in the cluster, when they start up, they open up a connection to the broker. Once connected, they can do whatever they want, right? But there's no way for the broker to get into that service. The service has to go to the broker first. That's the best kind of security, is the one you don't have to worry about, right? So in this case, we're reducing the surface area for compromise or for hack to almost nothing, right? It's very, very good in that respect. So it's faster, it's better results, more secure. What's not to like? So this kind of stuff is very interesting. I can't wait for the broker to be more real, and I can't wait to show it to you next time. I appreciate your time today, everyone. I'm happy to answer questions now. I hope you're all staying safe and healthy, and we're about to enter for a lot of organizations, a lot of countries and so on. It's about to be a second or third wave. I think we're in the 20th wave here in the States. So, I'm rooting for y'all. I miss you. I wish I could have been there in person. Perhaps next time. Let's see what questions we've got here. Okay. Okay, now we got some questions. Yay. Do reactive stream patterns still work well with Spring Cloud gateways? Absolutely. Spring Cloud Gateway is built on reactive streams. It implies reactive springs. Yeah, streams. Reactive springs. It implies reactive streams because it is a reactive stream API. We couldn't have built it as well as we did without reactive streams, right? What is the best protocol for inter-service communication when they're not reactive? Is RSocket meant for reactive apps only? I think I don't know. I don't even know if it's possible to use RSocket without having a reactive API. I don't know. I mean, if you're doing HTTP and you're okay with that, I don't know. I would maybe Grpc as a second place, because you can use that in a non-reactive fashion. The other thing that you might want to consider is that like if you're able to just tear out all of your APIs and your coordination between services, and you're able to go full bore, like refactoring mode, try embracing a different architecture, the tell, don't ask architecture. So here, every service, instead of asking for other services data, instead your service advertises its state to other services, who then maintain their own view of the system, right? So let's say there's an order that's been fulfilled, right? Well, every other microservice needs to know about that order in some way, but it's different. It's unique for each one. Maybe the fulfillment service needs to know where to start sending a truck with a package, right? Maybe the receipts billing service needs to account for that, to reconcile that or whatever. So each one has their own definition of why that event is important. So you say, hey, I've gotten a new order. I'm advertising that order to the system, and the rest of the system can get that event and they can process it if they want or not, but they keep it in their own database. They keep their own view of the world. So if a record is deleted, you advertise that. If a record is added, you advertise that. And each microservice reconciles that update in their own way into their own service, and using their own data model, right? Their data model might be Neo4j, a graph database for one service. It might be a full text search for another. It might be SQL database for yet another. It depends on the use case of that thing. The result of that is you're not asking for anything from anything anymore, right? All the things are telling you what the updated state is, and there you can just reset your view of the world. You can update your database accordingly. Obviously, this goes naturally with event sourcing, and it goes naturally with CQRS. So maybe you consider that. In that case, it doesn't matter if you're not using reactive APIs. In this case, you just use messaging. Everything would be over Kafka, right? And so you might get a lot of the benefits there of decoupling through this absorbent sort of buffer that we described in reactive APIs. But again, that's just as big a bite as moving to reactive, I suppose. So Okay. Is your reservation flux? I'm sorry. In your reservation flux example, would you still combine would you still combine this with Spring Cloud Circuit Breaker or Resilience for J, or think the helper method like timeout and back off or not? Great point. He adds, thanks, mate, big fan. I appreciate that, by the way. Great point. I didn't even mention Spring Cloud Circuit Breaker or Resilience for J. If I'm honest, if you had to just choose one, I would choose Resilience for J. Resilience for J gives you 4 key abstractions which work perfectly with reactive APIs. It gives you timeouts. It gives you retries. It gives you circuit breakers, which is to say, if I make a request and the request fails a successive number of times, I want to have a fail fast mechanism that returns a default value and then stops subsequent requests from making the same faulty request because it'll just fail for the same reasons. That's a circuit breaker. And there's also a that thing bulkhead where you can ensure that the client doesn't dedicate more than a certain number of threads for a particular request. Right? I'm not even sure if I really understand the value. I haven't thought about this enough, but I never really understood what the bulkhead is supposed to buy me in a reactive application. But either way, you can use those. Yeah, those are fine. Somebody mentioned that Hystrix is dead, right? So that's true. It's still usable. It's just we don't recommend it, nor does Netflix. Are there any valid use cases for which you will favor REST template over web client? Yeah, I mean, so again, you can use REST template to talk to a reactive service if it's HTTP, right? You can have a non-reactive client talking to a reactive service, and vice versa. You can have a reactive web client talking to a Spring MVC servlet-based application, because HTTP doesn't understand back pressure. It doesn't understand these concepts. So it doesn't care what client you use. It doesn't matter how efficient your threads are on either side of the network protocol. So you can use REST template, but for me, the web client is much more flexible. And now, one of the things that was kind of a problem for me in web client was for a couple of years, the support for file uploads was kind of a best effort, not exactly a purely reactive thing in the reactive case, in the web client case. But apparently that's just been fixed in the last 6 months. So I have literally no reason why I have no reason to not use web client. I would use it every time, put it another way, because it just seems like a cleaner, more fluid, more flexible API. But I hope I did mention that there are some use cases where I wouldn't use reactive APIs, right? So, anything algorithmic, Fibonacci series, in cryptography, whatever. Those things are not going to be inherently faster just because they're running inside of a reactive application. You need to make sure you put those in a separate thread pool because they're going to bog down the system. And you can't, security, you have to do it, right? I'm not saying you don't, but make sure you cordon that off. Beautiful demo, Josh. Yay for Active Spring. Sure, thank you so much. I appreciate that. Would you be able to give some real world scenarios where you may choose RSocket over Reactor? RSocket isn't where I may choose. You mean RSocket in lieu of Spring's Reactor or RSocket on top of Reactor? RSocket is a protocol, it's a network protocol, and the Java binding is based on Reactor. So it's kind of like RSocket is to Reactor and WebFlux as HTTP. Sorry, RSocket is to Spring as HTTP is to Spring web client, right? You can do both. There's a protocol and a client story for that. So yeah, media streaming seems like a win. Anytime where you have, in general, reactive APIs, anytime you have anything that would otherwise dominate a thread on the server side is better done in a reactive API. So chat notifications, telepresence, game updates, state, stock tickers, anything really, almost anything besides give me 8 records of JSON will probably lend itself to longer streams. Or even just if I have 8 trillion records of JSON and I want to just stream it all down, I can't afford to select all into memory and dump it all at once, so I have to stream. That works great as well. Okay, in a Kubernetes deployment, when we might have multiple instances of each service, how services can communicate using RSocket, considering that the connection remains.
Cycling, my legs have gone.
Huh? So how services can communicate using RSocket, considering that connection remains open forever, and it will lead to hotspot problems. Do we need Spring Cloud Gateway as an RSocket broker for this? And any update when that project goes GPA? GA rather. Yeah, so that's where you use like broker. That work that was in Spring Cloud Gateway for RSocket has been subsumed by this larger reactive reactive foundation effort, along with the work of Facebook and Alibaba and so on. So I don't have an update on when that is, but I expect we're going to see an update sometime this year on its state. Maybe it's an RC, maybe it's a beta, I don't know. And we'll start ramping down next year. We just got RSocket 1.1, let's say. Don't quote me. I could be wrong. 1.1 out the door, and there were some other things on which we were gated. And but the broker is. It's not that we don't have a working broker. The problem that we had when we went into the broker was that we had 3 working brokers, and we had to pick the best and build from the ashes the biggest and the best of the options. So that's the work that's been done for this year, and for most of this year, it's been about consolidating and building. Amazing stuff. Great demo, great tech. Thanks, Josh. Yeah, sure. Thank you. Amazing demo. Many thanks. Cheers. You're welcome. Thank you. Awesome demo. Thanks. Great demo and explanations. Thanks, Josh, for this. Thanks. Great talk, Josh. Thanks a lot, Josh. Okay, good. I appreciate all that. Questions. Let's see. Hey, Josh. First of all, thank you very much for this great demo. I want to ask, do you see the future of cloud-native Java still strong? I myself am a Java enthusiast, considering the rise of Go languages that have faster compilation as opposed to GraalVM, bootstrap faster in a containerized environment. Yeah, I mean, Java has the richest ecosystem, and actually think about this wonderful situation we're in right now. It's 2020, nearly 2021, and right now we're I don't know, about a year away from Project Panama, which gives me the ability to talk to native APIs, like the Panama Canal, a bridge, right, a connection. It gives me the ability to talk to native APIs in a very consistent way. As a person who did a lot of J&I through C++ headers, or talking to C code or to Objective-C code, I don't want to do that again. But Project Panama looks like it's actually going to make interop with native APIs, including managed memory, as easy as it is for people who are writing code from Python or Go or C++ or Objective-C or Swift or Rust or literally everything else. So once we have that, my goodness, I mean, just think about what we could do. The other thing that we're going to have is Loom. We're going to have green threads, right? And so Loom will give us the ability to be much more resource efficient. Well, suddenly, now I've got the ability to talk to POSIX and to talk to the kernel, and suddenly I've got the ability to handle tens of thousands of requests per second. I could build Kubernetes, right? The things you could do in Java are just going to get more impressive, not less. Right now, Java still dominates all the infrastructure on top of the platform. So the platform itself is probably Go these days, Kubernetes, Cloud Foundry, etc. I think even Heroku eventually moved to that, right? It used to be Ruby, by the way. It used to be like 10 years ago, if you asked all the cloud platforms, they're using Ruby, which is crazy. But now it's, I can only see Java becoming more useful. And by the way, GraalVM is now slated for inclusion or it's going to be rubber stamped, it looks like, as something called Project Layden. And Layden will be a native image format of some sort, hopefully bearing a striking resemblance to Graal, since that's where the industry is already kind of converged. That'll be in the JDK proper. So imagine in a few years, we'll have green threads, we'll have the ability to talk to native APIs, and we'll have the ability to create lightning fast native images that start up in no time at all in your containers. I can't believe that's Java. I can't believe that's where we're going to be before we hit 30 years. We'll have all those things in place. Perhaps in the next 2.5 years. Who knows? And in the meantime, Spring Boot and reactive-based applications are more memory efficient than, for example, the non-reactive APIs. So they're super fast. You can see, even though I'm zooming, even though I'm screen sharing a large 34-inch monitor on Zoom, even though I'm doing that, you can see my applications routinely started up in a couple of seconds, usually 1.5 seconds, or whatever, something like that, on both sides. So it's fast. Things are really fast now. Yeah, and by the way, check out Kotlin if you want to see. The other thing so we have all the runtime characteristics. Like I said, all these things are starting to apply to Java. But when it comes to syntax, well, obviously syntax, Java is it's as good as it can get given the constraints it has. But there's other languages out there, and if you're looking at something like Rust, you're like, oh, I wish I had something like Rust or Swift or whatever. Well, check out Kotlin. It is really sweet, and it makes reactive APIs even nicer. Oh, thanks, Josh, for answering. Oh, that's very kind of you, Filippo. I appreciate it. Very, very kind. I hope you all got something out of this. As always, my name is Josh Long. I'm Josh at joshlong.com and at StarbucksMan on Twitter. Don't hesitate to reach out to me. You know, if you have more questions, I'll happily hang out, but otherwise, happy to wind down. Smashed it, man. Appreciate it. Do I see Project Loom? Do I see Project Reactor using Project Loom internally to avoid context switching and solve the debugging problem? Yeah, I think it'll be yet another kind of scheduler. I think that would be very practical. Yeah, I don't know what the specifics are, but I assure you the Reactor team has, you know, they're on it, right? They're aware of the awesome possibilities. So here's hoping. If you're on Twitter, find me there. I'd love to get this conversation over with.
I guess that's a wrap. Cheers, Josh. That was very inspiring, and yeah, learned lots tonight from that. And yeah, thanks a lot.
Wonderful. I'm glad you enjoyed. I appreciate it. And I guess we just hang up. You hang up first. No, I'll hang up first. No, you hang up.
All right. Good evening.
Good night, everybody.
Bye.